in this lecture we shall see how we can model register banks or register arrays or register files. Now, you have seen some examples earlier, like we saw how we can design the data path and control paths for certain designs like multiplier, GCD computation, etc. Those designs were pretty small designs, but even there we saw there was the requirement of several registers. Like for a multiplier you needed a register A, Q, M and so on. But you think of more complex systems, you think of a computer, a processor. So, inside a processor there will be much larger number of registers. Well, a modern day processors can have 64, 32, 128 registers, very large number of registers. So, how to implement those registers? Registers you can implement as individual reg 0, reg 1, reg 2 like that, individual variables, or you can also store them similar to a memory, model them like a memory and just allow the synthesis tool to synthesize the register bank as an array of hardware registers, because usually register banks or register files, they are not implemented using memory technology, but they are implemented using flip flops which are much fast, they are much faster, static RAM technology. Okay. So, the topic of this lecture is modeling register banks. So, the first question is, what is a register bank? A register bank, which is sometimes also called a register file, it is a group of registers. Like let us take an example. Suppose I have a register R0, I have a register R1, I have a register R2, I have a register R3, let us say 4 registers. So, I can use them individually in a program R0, R1, R2 or R3, but suppose what I say is that, well, let me group all the 4 registers together and let me call this a register bank, right. Now, in this register bank from outside I can specify a register address, a 2-bit register address, because there are 4 registers, in 2 bits I can specify R0, R1, R2 or R3. So, with this register address I will be selecting one of the registers and then I can either read or I can write into that register. This is the concept of a register bank. So, just to summarize, I can use the registers individually as variables and read and write from them individually by their names, or I can treat them as a group just like a memory element and I can read and write from there. Okay. Fine. Now, a register bank, as I said, is typically used in a processor, in a computer, to store the registers which are typically used for temporary storage of data. Now, as an example, there is a common processor called MIPS 32. This is an example of a reduced instruction set architecture. Here there are 32 registers and each of the registers are of 32-bit size, and these 32 registers are referred to as R0, R1 up to R31. Now, as I said, in Verilog you can either define 32 variables and implement them as independent registers, or you can implement them as an array of registers which will be very similar to modeling memory. Well, not only this, a register bank typically supports some other features like concurrent access. As an example, for this MIPS 32 processor that I was talking about, here the register bank is so designed that you can carry out 2 register reads and 1 register write in every clock cycle, which means 3 operations can be carried out concurrently on the register. But of course, suppose you are writing into register R5 and you are at the same time reading from R5, there will be an inconsistency. So, you should not read and write into the same register, but you can read from R5, read from R10 and write into R8. That is possible, and these 3 things can go on in parallel. Okay? Fine. So, we shall be showing some alternate designs of register bank which will support this kind of concurrent access, that means 2 reads and 1 writes at the same time. And of course, I have made this assumption, same register is not read and written together, because if it is so, there will be some conflict. So, pictorially our register bank, well, the MIPS 32 register bank, 32 registers each of 32 bits will look like this. There will be 3 access ports, 2 read and 1 write. In the read ports, what do we have? We have a register number, that which register I want to write. Because there are 32 registers, you need 5 bits here. Similarly, for the second port, there are 5 bits. This will actually be source register 2, not 1. This is 1 and this is 2. Okay. And so, once we have specified the register number, we can read them and the data will be available over these 32 bits. And on the other side, when you are writing, so again you have to specify which register you want to write, that is again 5 bits, and the actual data you want to write, 32 bits. So, there are 2 read ports and 1 write port. Fine. Let us take a simple example to start with. Let us say we do not have 32 registers, but we have only 4 registers, small number. So, because it is small, we can declare the registers individually. This is what I am assuming. So, how is our declaration? Our declaration is like this. So, in our register bank, there are 2 read ports and 1 write port, as I said, read data 1, read data 2, write data. So, what are these 3? This is read data 1, read data 2 and this is write data. And we have source register 1, source register 2 and destination register. This is here, source register 1, source register 2 and destination register. These are all. So, in this case, because there are 4 registers, these will be 2 bits each, and of course, write and a clock, because read is by default. Let us see the variable declarations. Clock and write will clearly be inputs, and source register 1, 2 and the destination register, they will be 2 bits because there are 4 registers. Write data, read data 1, read data 2, all are 32 bit quantities, and for read data, since you are reading and assigning, they are defined as reg. Okay. And the data you want to write, that is coming from here, and that is declared as input wire. And we define the 4 registers like this, R0, R1, R2, R3. So, you will be using a set of always blocks, very simple. This is the always block for the port 1. So, you check always whenever something is changing, case SR1, source register 1, whatever is SR1 is 0, 1, 2 or 3, because it is 2 bits. If it is 0, then the value of R0 will go to read data 1, if it is 1 then R1, if it is 2 R2, if it is 3 R3. But if it is not, if it is other than 0, 1, 2, 3, because you see these are Verilog variables. So, the Verilog variables can also contain values which are z or x, not necessarily only 0 and 1. Okay. So, if it is anything else, then read data 1 will be assigned the undefined value xxxx. This is for the first read port. Similarly, for the second read port, same block, but here case SR2. Depending on SR2, R0 will be assigned to read data 2 or R1 or R2 or R3. This is for the second port, and third one is for write, and writing is in synchronism with a clock. Okay. So, whenever there is a clock, then only we are writing. If write is active, then you see what is your destination register. So, if dr is 0, you write into R0, if dr is 1, you write into R1 and so on. So, this is a very simple description of a register file or register bank containing 4 registers, where the registers are defined individually, independently. Let us see some other ways in which we can define or declare such register bank definitions. So, this, as I said, this way enumerating the values is feasible if the number of registers is small. Just imagine if there are 32 registers, it will be too tedious, you have to write 32 lines here, 32 lines here and so on. Okay. Now, let us again keep this number as 4 registers defined independently, but we are using an alternate way of implementing the read ports. Like in the earlier case, you see the read ports were implemented using an always block and a case. Okay. Here we are implementing them using assign statements. The first part is identical, there is no change here. Just only thing, because here read data 1 you are not assigning inside an always block. So, we have not given reg here, only output, right. Here this is like an if then else kind of a statement using the conditional operator. What does it mean? It means if SR1 equal to 0, if this condition is true, then R0 is assigned. If not, otherwise SR1 equal to 1, if this is true, then R1 assigned. Otherwise, if it is true, then R2, otherwise if it is 3, then R3. If nothing matches, here you have given 0, or you can give undefined also if you want. Similarly, read data 2 is identical with SR2, and the third block is identical again with a clock for writing. So, this is how you can implement a register file, and you can do reading and writing like this. Let us now come to a complete register file like MIPS 32 by 32. Here let us see how we can model it. Here we are using an array like a memory. So, the arguments are the same: read data 1, read data 2, write data, source register 1, 2, destination register, write at clock. The difference is here SR1, SR2 and DR will be 5-bit quantities, because there are 32 registers and 2 to the power 5 is 32. That is why we will be needing 5 bits to represent a particular register, right. So, this is how we are declaring our register file, just like a memory. So, each word contains 32 bits and there are 32 locations 0 up to 31. So, for reading we can simply give assign statements: read data 1 equal to reg file, this SR1 as the index. For the second port, reg file, SR2 as the index. And for write, always at POSH clock, if write is active, write data goes to reg file dr, simple, right. So, in a behavioral way it is very compact and simple to specify a register file like this. Now, in addition let us add another facility. Like you see, when you have a register file, means often there is a facility using which you can reset the registers from outside. Resetting means, let us say there will be a reset signal, control signal. So, if we activate reset from outside, all the registers, they will be initialized to zeros. Okay. this is what you want. So, in the next version is just a modification of this. Here we are saying this is a 32 by 32 register file, but with reset facility. So, what is the change? The change is there is a variable additionally included here called reset, which is also an input variable, and we have declared an integer k. The rest is the same. The way you read from the register file, there is no change, just in the previous one exactly the same, but while writing there is a little change. This is synchronous. So, whenever there is a clock, you first check whether reset is active or not. If reset is active, then in a for loop you go from k equal to 0 up to k equal to 31 and initialize all reg file k's to zeros. So, all the registers are initialized to 0. But if reset is not active, you come to the else part, you see if write is active or not. If write is active, then you write this data into reg file dr, right. So, this is how it works. Now, let us look at a test bench to verify the reg bank V4, which means we are just using the register bank with the reset facility, the last example that we took, this one, right. This one, let us write a test bench for it. So, what we have done, let us see. So, we have instantiated the register bank, we have given a name reg. So, we have not changed the names, you can change the names if you want. So, read data 1, read data 2 were inputs. Now, here they are output, they are actually coming out. So, in this case they will be wires, but wherever you are writing they will all be reg, write data SR1, SR2, DR, write, reset, clock, these will all be reg, right. And we are defining an integer k. Let us see what we are doing here. We are initializing clock to 0 and always at 5 clock equal to not clock. This means again we are using a clock signal like this. We start with time 0, so at 5 we toggle, again after 5 we toggle, again after 5, again after 5, like this. So, after time 5 we are toggling the state. So, our time period will be 10, this will be our time period, which is 10. Now, let us look into the timing of this signal, what you are actually doing. These are the edges, right. Now, what we have done, now in this initial block we are actually creating the reset signal. So, here of course, we have specified a dump file and the variables to dump. We are we are activating reset at time 1, write is 0. So, that write does not take place, and after a gap of 5 we are setting reset back to 0. So, what will happen? This is time 0, right. So, if you look into the reset signal, reset initially it was undefined. So, it was, so at time 1 it was undefined, let us say this is 1, at time 1 you are setting reset to 1 and it continues 1 up to time 6, at time 6 you set reset to 0 and after that you do not make it 1 again. So, what does this mean? This means that when the first clock edge comes here, out here, your reset is 1. That means, initially all the registers will be reset to zeros, right. This is what you do here. And then there is another part of the test bench. You see here from there is another initial block, so that again it starts from time 0. So, after a gap of 7, you see what you do, you go in a for loop 0 up to 31, you put k into destination register, write data 10 into k, you write it, write equal to 1. 10 into k means register number I, you are storing the value 10 into I. So, register 0 will get 0, register 1 will get 10, register 2 will get 20, 3 will get 30 and so on. So, let us say we initialize registers like this. Okay. So, write data equal to 10 into k, and there is a delay of 10. After delay of 10, I set back write to 0 and repeat this again, this is repeated. So, what does this mean? You think of the write signal, what happens? Write becomes 1 after a delay of 7, and after a delay of 10 it again becomes 0. So, what does this mean? So, how will the write signal look like? Write will become 1 at time 7, 7 is where this is 5. So, it is somewhere here. Before that it was not specified. So, write will be 1 here, and it will remain 1 for a period of time 10, that means it will remain 1 till here, then it will again go 0, right. So, like this it will go on. So, when the next clock edge comes, it will be high and write will take place. So, again when you go back to the loop, so again this will be 1, again after time 10 it will be 0, again it will be 1, like this it will go on. So, it will be writing will be taking place with every clock edge one by one. Okay. So, in this loop the writings will take place. Well, after the writings are done, here just as an example, here we are just observing the contents of some of the registers. So, what we are doing, k equal to 0 up to 31 again. Here we are reading 2 registers at a time, and here k equal to k plus 2 is skipping by 2, okay? K equal to 0, 3, 2, 4, 6, 8 like that. And source register 1 we are initializing k and SR2 k plus 1, and we are displaying the values of SR1, read data 1, SR2, read data, whatever data is stored there, and we are printing it like this, reg within bracket register number equal to data like that, and we finish here. So, when we just run this, just if you look at the simulation output, like whatever is getting printed by this display, we see something like this. You see what we expected is actually that. So, each register is stored the twice the value, register number 8 10 times the value, sorry. So, 8 contains 80, 13 contains 130, register 23 contains 230, 28 contains 280. So, it is actually 10 times it is stored. Okay. Now, if you also see the timing diagram, so I am showing you 2 parts of the timing diagram. This is the first part where reset has been activated, initially reset has been activated, and then you are writing the data 10 into k. You see the register number dr is changing 00, 01, 02, 03. So, the write is continuously active because it is going low and immediately going high. So, that you are not seeing here, write is continuously active. So, 0, 1, 2 with the clock edge writing is going on. Okay. And towards the end, this is towards the end of the simulation, here you are reading the values. You see SR1 and SR2, 0, 1, then 2, 3, then 4, 5, 6, 7 like that, and you see the read data 1 and read data 2. For 0, 1 the data are 0, 0, 0 and 0, 0, 0 A, which means 0 and 10. 2 and 3 are 0, 0, 1, 4 means 20, and this is 1 E means 30. For 4 and 5 it is 2 8 hexadecimal means 40, 3 2 means 50. So, like that the data values are actually coming. So, you see in this way you can model a register bank or a register file, and you have seen through the test bench that actually you are able to read and write together at the same time. Okay. So, we will see some more examples of register banks later when we talk about more complex systems that involves something called pipelining, but this we shall be discussing later. Okay. So, with this we come to the end of this lecture. So, in this lecture whatever we have basically seen, we have summarized how we can define register banks or register files, and how we can have multiple read and write ports. You can read from the register banks, you can write into the register banks, and how we can write a test bench and simulate the design using the test bench. So, we shall see later, as I said, that we will be using some more complex designs where we will be using this kind of register files as a basic building block. So, whatever description we have given, something similar to that, that will happen as part of the main module descriptions therein. So, with this we come to the end of this lecture. Thank you.